Okay, so let's see how we can approach this problem. Now, this problem asks us to reduce the block diagram into a single transfer function using block diagram reduction. Now, how can we approach this problem? Now, whenever we are trying to reduce a block diagram using the diagram reduction, we need to think about some actions that we can perform. So these are common actions like blocks in series, blocks in parallel, moving summing junction or moving takeoff point, and a standard feedback loop. And the most common ones that you should start thinking of is blocks in series, blocks in parallel, and the standard feedback loop. So you need to ask yourself, in my block diagram, can I perform these particular functions or actions? Do I see any blocks connected in series or any blocks connected in parallel or any standard feedback loop? If so, we can apply their operations directly and easily. So let's see how we can apply this in our question. So we need to see if we do have any blocks in series, in parallel, or a standard feedback loop. Now I can see here that we do actually have these blocks connected in parallel. Now how can we know? We can see that actually they do share a common node and the arrows are actually the same. So this is definitely not a feedback. And this is basically, or these two gains are parallelly connected. So, okay, now I can see that I have some blocks connected in parallel. What kind of operation I can take? Well, simply the operation is addition. So I need to add these two gains together. So instead of G2 and G3 separately, it will become as G2 plus G3, as straightforward as this. So now let's see our same block simplified with G2 plus G3. We can see here, now this is our block. We can see now this feedback is gone because it simply was connected in parallel. I do not need this basically summation anymore. Now what else do I have? Yes, so I have reduced kind of the block a little bit by having both G2 and G3 connected in parallel. Now let's further reduce or simplify the diagram. Now again, I want to ask myself, are there any blocks connected in series or in parallel or in a standard feedback loop? Now, if we pay attention here, we can see that we actually do have here a standard feedback loop. So we actually have this gain, which is G6, and we also have an H here, which is actually a unit function. So if I want to use the standard feedback loop, basically converting it to a transfer function, I can simply say that this is G6 divided by 1. Now here plus or minus, it will depend on the operation I have here, because I do have here subtraction in the equation, then it should be actually the opposite. It should be plus. Now G6 times H, in this case my H is 1, so it would be G6. So this is perfect. I have further simplified my block diagram here using this standard feedback loop action. So I can see here my block diagram further simplified. Now, let's ask ourselves again, do I have any blocks connected in series, any blocks connected in parallel, or if I do have a standard feedback loop? Now, what we can observe here is that we do not have these actions directly, so I need to think about the other actions that we have. And of course, these are not the only actions. There are actually other actions, but these are the ones that are or can typically used. And in order to prove these actions with the operation, I will provide you, or I have provided you actually a link in the description box. Now, let's see what we can do here. Now, I can see that if I pay closer attention to this kind of loop, I do have here a feedback, right? But the only thing that is actually preventing me to considering it a full feedback is this G4. So I want kind of to move G4 here, or I need to move this arrow actually, or what we call as a takeoff. I want to remove this takeoff and put it here, somewhere here, in order to have this basically feedback. And then I can perform the operation directly. Even if I move G4 here, I can actually have G5 and G4 connected in parallel, as we are going to see. Now, I can perform this. So what I'm going to do is that what I want to do here is to move my take-off point. Now, is it downstream or upstream? Actually, I'm moving it downstream. Now, you can think about it that if I'm moving the block into the right side, or kind of if I'm moving it into this way, then this is actually downstream. So this is I'm going to change the highlighter. It actually looks. Okay, so let me change the color. I want to move my takeoff point downstream. All right, I don't think that this one is better, but anyways. So how can I move this actually here? So this is what we call as downstream, moving this arrow to here. How can we do that? Now, the operation here, or the rule tells me that I need to divide. I need to divide whatever I'm moving through. I'm moving G4 through G2 plus G3. So what I need to do here, if we go to this action block diagram, I need to have my G4 divided by G2 plus G3, because I move this arrow from here, right? So I had my G4 here, but I'm moving it here, right? Downstream. So I move from here to here, and I'm moving it through what? Through G2 plus G3. That's why, in this case, if I'm using this action, move takeoff point downstream, I know that I should actually divide. So in this case, we simply divide the G4 by G2 plus G3. And now what we can see here is that we end up having actually our standard feedback loop. So if we look into this, pay closer attention, we do have here a feedback loop. So how can we actually, what kind of operation I need to perform in a standard feedback loop? I know that this is straightforward, G1 divided by, or G2, sorry. This is actually my gain, plus G3 divided by 1 plus, now H here is G1 times G2 plus G3. Now, do I have anything else? Now, do I have blocks connected in series, blocks connected? So again, we need to keep these actions in mind, which are blocks in series, blocks in parallel, and the standard feedback loop. Now, I can see here is that I do have other blocks that are connected in parallel. So we can see that they do share the same, if we pay closer attention, they do share the same actually nodes and the same arrow direction. So they are connected in parallel. So what kind of operation I can do here? We can simply, if I just want to change the color, okay, so we can simply add them because they are connected in parallel. So therefore, we end up with basically the following blocks simplified in this way. So we do have the block from basically the transfer function, and then the second one from the parallel connection, and the third one, which is basically, we don't forget about it, from our first feedback loop. Now, we can see that we do have these blocks connected in what? Connected in series. So since they are connected in series, what kind of operation we need to perform? Easy, we need to perform multiplication. So we multiply all of these together in order to get kind of a single, basically, what we call it single block. And this is basically the gain of this block. So we can call this block as GE. And if I want just to have this, let me just kind of redraw it fast. So this is my R and this is my C, but I still have what? I still have this gain that I should not forget about it. So here we go. And again, I want to call this, just to make it easy, I want to call this G of E. So this means that my final transfer function, which is basically transfer, just gonna call it as FUN. So my final transfer function, which is C of S divided by R of S, is simply, so now what kind of action I need to basically perform? I can see that here I have a standard feedback loop. So I know that this is what? This is GE divided by 1 plus GE G7. And this is actually my reduced block diagram.